So it goes on. We've already seen this second order differential equation here with its coefficient terms of x. These are the ones that make life a little harder at the moment for us to find solutions. But I've already explained to you that given this one fundamental solution, e power x, which could easily be guessed also, the method of variation of constants is very useful. And let's just try and use it and also look look what we get in detail. Well, the idea is, since this term, even if I use an arbitrary constant factor C1, is a solution to this homogeneous differential equation, we know that taking its derivative, its second derivative, and filling it in, we always get 0 on the right-hand side for any value of x. So that's true, and that's why it's the first fundamental solution of this equation. Now, variation of constants means take your solution parameter and replace it by just an unknown term of x, which, just for clarity, I call capital K. So we rename C to be K, just to make clear it's no more a constant. It's not a constant anymore. Now it's a term of x. And now, this time, I call this y2 because it's the second fundamental solution that we expect for this differential equation to exist. We just use the product rule of differentiation to find the first and second derivative of this approach. And now, doing so, I do the usual thing. I take the derivative of k of x, which is just k prime of x. So allow me to leave away this of x notation because it's just a compact way here. Then leaving this alone, the second factor, e power x, plus other way around, k times e power x prime, which is still e power x. And so I can put this in these factors in parentheses, which are then k prime plus k as a total factor with e power x. So that's it. And taking the product rule another time, using this as my first factor, I find this gets me k double prime plus k prime. I think I even explained this before, times e power x, and then plus, leaving this alone, times e power x again. Once more, put e power x to the right and find in your parentheses this time k double prime plus k prime plus another k prime. So it's two times k prime plus k, and that's it, times e power x, and we're done, because we only need the well, you could say derivative number 0, number 1, number 2 in order to fill into our original differential equation. This is what we do now. Look here. First of all, I remove these parentheses, so I get x times 1 plus x times x, so x plus x squared is my factor. With the second derivative, which is here, I take it over. It's k double prime plus 2 times k prime plus k in parentheses. And as you see, I just left away the factor of e power x for a simple reason. We are trying to solve a homogeneous differential equation where we know that in the end, everything must be 0 for any value of x. And since we know that an additional factor of e power x, here it is. I'm sorry, I didn't leave it away, but I can move it to the right. And then I can argue in the end that this factor never gets 0. It's always greater than 0, as we know. So by the theorem of zero product, we know that the other factor must be 0. That's it. Okay. So we are here. This was k double prime plus 2 k prime plus k from here. Just ignore the blue color now, for now. Next term, minus these parentheses, x squared minus 2 times. Now I take over this, k prime plus k, still times e power x, which I move to the right. And then finally, minus x plus 2 in parentheses, this time times k only, because the y, which is our unknown function by approach, is just k times e power x. E power x moved to the right. So that's all. And now you see, looking carefully, and also you can expect something special to happen, namely, you can expect your k replacement unknown to disappear, to vanish in this equation. That's something that happens due to the fact that the e power x factor is itself a solution of the whole differential equation. It's an interesting effect. Now you see what I have. It's not so easy. You just have to look carefully, and now you find, well, how is it? The factors of x are important. We get x times k, and then if we look here, we have negative x times k, right? Positive x squared times k, here it is negative x squared times k. And this is much for the same reason, which leads to the fulfillment of the equation inserting e power x alone. So that's really the catalyst effect of e power x using variation of constants. Well, removing k itself out of this equation. Let's go on, checking. Did we have this? Yes, we did. Look, negative 2 times k, and here it's, oh, is it? Yeah, which means positive 2 times k, and here it's negative 2 times k. So altogether, I can cross out every appearance of k, and since nothing remains here, I can also cross out the factor of negative x plus 2. So this is this goes away. But here it's important to keep the other terms. So that's what I well, what remains? It's these this factor of x, I just resorted x squared plus x parentheses times k double prime plus. Now look carefully. We have taking everything together. Yeah. Okay. What do we have? We have how comes the positive sign about? I'm just thinking. Okay, here it is. So this is x squared. What is it? X squared times 2 times k prime. So I have a prefactor of 2 times x squared, but here I have negative x squared times k prime. So pulling this together, what remains is just once a positive x squared factor. That's it from these two contributions. Then also I have x times 2k prime. This is why I put 2x into the parentheses times k prime in the end. So that's this linear contribution concerning x. And additionally, we have this negative 2 times k prime, which I put as a positive 2 inside the parentheses. So you can check it all together. This is the prefactor for our k prime. But k has disappeared, and that's the reason why this transformed second order differential equation now may be easily transformed to a simple first order differential equation by just taking the substitution that our, well, let's just call it capital L, whatever, alphabetically. L of x should be the first derivative of k of x. K of x is still unknown, and so is L of x, but we just replace k prime for L. Now the brand new unknown is called capital L. And since the second derivative of k is then also the first derivative of L, you see, if I take a prime symbol additionally here, so I get L prime equals k double prime, I may replace this one for L prime and this one for L, and now I have a certain term of x polynomial times L prime plus another polynomial times L equals 0. So now that's nice because we can easily normalize this first order equation. Let's do so that L prime, just dividing by this term, which I must say should not be equal to 0 or -1. Why? Because we do not want to divide by 0, or we even can't divide by 0. So that's again a case where we have to check this restriction afterwards. I will even forget it probably, but you should check it afterwards. And in the end, it will turn out, as far as I know, well, 0 is indeed a problem, but this will explain itself. This will be self-explaining because the solution that we find will be a function which is not even well defined at x equals 0. It has a definition gap at 0. So that's what we expect then. But for the -1, there will be no problem in the end. So this is a little tricky to argue about these preliminary restrictions. Let's just leave it away. Now we get L prime equals this polynomial over the other polynomial times L. And please don't forget a minus sign before it, because I have to move this to the right-hand side first. So this is what I just did is almost separation of variables, our interesting simple method for solving first order differential equations. And now what I have is the L over the X, as you know, which is the quotient notation for L prime, equals this interesting rational function with long ago we've been concerned with rational functions, how to transform them, you know, how to perform a polynomial division first, and then secondly a partial fraction decomposition. That's what we do, that's what we used to do in order to solve integrals over such fraction functions, over such rational functions, which is something we've been doing for quite a while when solving integrals. You remember, you can look back to the corresponding video section, series also. Now, also I will put this differential of x to the other side, and I will divide this whole equation by L. Again, I should say, for this purpose, L should not be equal to 0, so that's still another restriction, but also this restriction, let's say it's preliminary, and I don't even know whether there are any zeros of L, but let's not care about this. So what do we get in the end? If I abbreviate this fraction, this rational function, just by capital R of x, let's see. Well, first of all, this is, well, I should call it side. Let's say SC for side calculation, right? I don't care what I'm putting here, how I'm calling it. Well, R of x, first of all, the polynomial division is simple. We can just do it. Look here. The denominator is x squared plus x, and x squared is here and x is here, so we can just move this apart and say x squared plus x divided by itself gives us an integer 1, while the other x plus 2 remains over x squared plus x to be, now this is a true fraction. Okay, and a proper fraction. You remember, this is called an improper fraction because the grades of yes, numerator and denominator are the same. This is the border case of a so-called improper fraction. But as soon as I perform my polynomial division, I get an integer part plus, or let's say a regular power part plus a proper function. But this is still too complicated to be integrated, which we have to do soon. Okay, so in order to integrate it, we still have to perform this so-called partial fraction decomposition that you all know. There's a very universal approach to it. First of all, you need all the zeros of the denominator. In this case, x squared plus x is easily factorized to be x times x plus 1. Okay, so I didn't even do this, I just do it in my mind. And so that's why I get these two partial fractions in sum. Okay, this is my approach. There will be some unknown constant capital A over x plus some unknown constant capital B over x plus 1. These are the two zero terms of the denominator. And this, we all know that by the universal approach, this is valid. We just have to solve it by putting this equation into a non-fractional form. I do so by multiplying with the main, the common denominator of, or the total denominator of x squared plus x. In this way, the numerator remains. I just, for clarity, I renamed it to be 1 times x plus 2. Golden color for the factor of 1 here. Red underlining for the constant. You will see soon I will perform a coefficient comparison, comparison of coefficients. I get my a times the other factor. You see the multiplying this, the factor of x cancels out, but x plus 1 remains. Plus here the other way around, b times x, the other factor, x plus 1 cancels out. So that's my fraction-free approach, and then I just have to, well, resort it a little bit. I get a times x plus b times x, putting x, moving x to the right. This is a plus b in parentheses times x, and also plus constantly a times 1, so just plus a. So what does it mean? It means the red underlined terms must be identical. This equation is demanded to hold for all values of x, so that's always the same procedure, comparison of coefficients. A equals 2, I can put this into the other equation, which tells us that a plus b must be equal to 1 in order to fulfill this. So then, since a equals 2, I get 2 plus b equals 1, and isolating b, b will be equal to -1. That's it. So it means this is our total decomposition of this interesting rational function. It is 1 plus 2 over x minus 1 over x plus 1. And this is easily to be integrated over x. So go back here. Well, imagine you would have dx move to the other, or let's just do it, okay? Let's just say dl over l is what we have, then equals negative our transformed fraction, which is 1 plus 2 over x minus 1 over x plus 1, in parentheses, times dx, and now we may perform an indefinite integral on both sides, here over L, here over x. As you see, also L may be considered to be just a regular variable, even though L and x are coupled to each other. They are coupled in a way which is given by this equation. And so that's why we may integrate on both sides and still get a valid result. So that's for explanation again, to use this separation of variables. Now, as we know, here the primitive function will be natural logarithm of modulus of L, so absolute value. L may also be negative, remember, equals, and now simply -1 integrated gets -x linearly. This one is plus just 2 times the natural logarithm of x, vertical bars, yeah, absolute value. And this one is still another modified version of a function which is reciprocal. So also this gets, aside from, look here, negative gets positive again, yeah, minus gets plus. And then we have a natural logarithm of the denominator x plus 1 with vertical bars. Please recognize that this is just a case for a really simple linear substitution, if you want. But it's just, you can say it's a horizontally replaced version of 1 over x. So that's clear. Okay, and now I must say, it's a matter of experience to decide whether any integration constant is needed here or is not. You will see much in the end. All that we want is to find another fundamental solution to this homogeneous equation. And since all these constants which appear while doing so will disappear again in the end, due to the fact that we may use a solution parameter to our fundamental solution. This is the reason why, by experience, we know that we can leave away most of these constants appearing during integration. So that's a little hard to explain in short. You just trust me at this point, okay? You could use them, but you would find that the only thing you reach by using them is everything gets more complicated, but much at the end, it simplifies again. So it's just unnecessary efforts to take, which I want to avoid. Okay, so let's leave this away. Now take the exponential on both sides, as always, to get rid of the logarithm. So here we get, first of all, we get modulus of L of x. Then now this is really very much in one step, which we did before. You remember, if I take exponential of this whole term, I can use all our rules of potency. So I can say, I can easily put this in product form, which is, roughly speaking, exponential first term, exponential -1, okay, e power -1, then times the exponential of the next term. And here you see, I can easily transform it to be, it is e power -2 ln modulus of x. Then I can put this 2 as an exponent here. You remember we had this before, and x squared is x squared. We can leave away the bars, the vertical bars. The ln is cancelled against the exponential. So what all that remains here will be actually, oh sorry, it's a minus sign before, so it will be x power -2. but also power of -2 removes the signature. So that means I get, what I would really get is a factor of 1 over x squared. So getting from here to here is some steps in between you might do by your own. Take your time, put it on a piece of paper, and you will find out. Okay, and then also the next factor will be just simply x plus 1. Well, honestly, there should be modulus vertical bars still here, but I also put these away due to the fact that in the end we can always use a constant factor which is arbitrary. So also this is a step of experience, not using vertical bars. Just allow me to do so. So that's roughly, that's what I get, and then multiplying this together, it will be 1 over x inside plus, as you see, 1 over x squared, and the whole thing times a damping function, which is exponential, or e power -x. That's not yet our result for the fundamental solution, because we've just found out L of x, ignoring quite a few things, like this integration constant, which is transformed to an arbitrary factor, and then even ignoring this one, even ignoring that we should take the modulus here. You just trust me, these are steps by experience which are allowed in the end. You could also say they are allowed afterwards, because they don't play any role. Anyway, we have to take the primitive to find k of x. And now you remember, by the substitution, L equals k prime, so k must be the primitive of L of x. And doing so, now this is also a little bit tricky. You would not, perhaps you would not at once see that the primitive of this term equals -1 over x times e power -x. In order to solve this integral, you would have to take some more steps, probably even product integration and so on. But well, you could also just believe me and say, okay, I can test it by taking d over dx of this whole term. Doing it by the product rule, you will find that exactly this will be the first derivative of this one. So it's just saving some time at the moment, okay? So we get our k, and finally we must go to our original approach, which has been using variation of constants, here has been y2 equals capital K times exponential, so times e power x. And this is, you could say, again, sort of a catalyst effect of e power x, which now is taken away out of our chemistry or our chemical reaction, mathematical reaction, well. So what we do is just multiply e power x so that it cancels this e power -x, and all that remains is -1 over x. So that's quite a simple result for much effort. But the reason for this effort has been, it is not so easy just to guess that 1 over x is actually the second fundamental solution to this homogeneous ordinary differential equation. And even this negative sign does not matter. I just to take it away. So finally, I can argue that all my crossing outs that I've used are justified by the fact that in the end, I can use an arbitrary linear combination of the two found, well, let's say fundamental solutions, so that the general solution of the homogeneous differential equation will be some factor C1 times e power x plus another factor to Z2 times 1 over x. So you see that these two functions are obviously very different from each other. That's typical for such an equation. And you can test it also. It's a nice idea to test it. 1 over x, just take the derivative, the second derivative, and go back to your original equation and find out that these polynomials, again, will cancel out perfectly for any value of x, and then fulfilling this equation, but much in a different way than this happened using e power x. So these two fundamental solutions are a so-called fundamental system also, which together make this second order differential equation solved completely. So, and there's a theory behind it. I must also add this, or I think I'll make a little break at this point.